Hello, everyone. We're extremely glad to have you all for a presentation on ranking-based dynamic hot sparing. Today, we talk about the learnings that we've had during implementation of this novel approach. I'm Hemant Gaikwad, and I work as a validation technologist for Dell Server Division. With me, I have Rahul Vishwakarma, who works as a lead for the Dell's Data Protection Division. So we have a very short agenda. We'll try to cover about the problems with the traditional approaches. We'll have a detailed discussion on the proposed approach and also be able to provide benefits that you could get by using this proposed approach over the traditional approach. So let's understand the traditional approach first. So sparing mechanism is one of the key factors to be considered for system reliability. However, configuring more spares than required or shortage of spares have their own limitations. In an event that one or more disk failures, you'll typically have disk shortages, which can increase the restoration time, thus impacting the system availability. At the same time, excess of spares has its own financial implications. Also, in the traditional approach, the drives are tasked to perform a set role. Certain drives are dedicated as capacitor drives, while certain drives would be marked as spares. So in most of the cases, the traditional sparing mechanism failed to achieve the dilemma of excess of drives or the shortage of spares. Because the first level of sparing method is to identify the fail or the failing drives in a RAID group and then replace it with a spare drive. Irrespective of whichever novel sparing method is applied, there is an inherent problem to these methods. The so-called bad drive, which is either a failing or a failed drive, is labeled as bad. So as such, all the drives in the storage system would just have two labels, good or bad, with the failing or the failed drive assertion made using any underlying statistical or threshold-based machine learning methods. This approach still has its own drawbacks. Most prominently, it is static in nature. That is a 0 or 1 way of denoting a drive as either good or bad. In this diagram, you could see that the drives, the coloring is just either white or black. That means the drive is either good or it either bad. So the problems with the traditional approach generally result in just two outcomes. One being aggressive, where the admins populate the system with more than required number of drives and preempt removal of drives which are yet to fail completely. And the other being regressive, where the admins populate the system with just adequate number of drives or less number of drives, resulting in higher downtimes. Now let's have a look at the proposed approach and what it does in terms of solving the problem statement. To overcome the problems with the traditional approach that we just discussed, what is needed is a smart sparing mechanism. A mechanism which is based on the degree of badness and helps in identifying which RAID group needs more attention and how to assign the spares. So there's nothing great with this approach, but using pure common sense of providing more attention where it's duly required. I would like to share a real life example here. So considering that this event is happening in India, almost everyone knows in and out of the game called cricket. But there's one lesser known fact. The first testicular guard, which is generally used to protect the groin area, was used in cricket in 1874. However, the first helmet was used in 1974. What it goes to show is that it took over 100 years for men to realize that the brain is equally important and does require more attention than we generally give. So going by the same analogy, the proposed method does dynamic automated configuration changes based on the degree of badness, or simply said, the degree of attention required. If you look at the blocks towards the bottom of the slides, you could now see that the drives have a way of um, denoting the badness associated with the drives, where the form of gray coloring shows essentially the varying degree of badness associated with the drives, which is unlike the traditional approach, which just shows it as good or bad. Okay, we shall have a detailed look at the approach in the subsequent slides and then understand how this proposed mechanism is going to help solve the problems with associating a degree of badness related to a particular drive, which is either going bad or it's just about to get bad or it's already bad. With that, I'll hand it over to Rahul to cover the next few slides.
Thanks, Iman. So now let's start to understand what is a well predictor. So well predictor is a very simple thing which is used in the machine learning classifier, and where we have to do a multi-probabilistic prediction. So this is quite simple, as you can see from the pseudocode, that what we have to do is like first we have to use any of the machine learning scoring classifier and we have to pass it to isotonic calibrator. So that helps you gets the value of the P0 and P1, which are the boundary value of the multi-probabilistic prediction. Now let's try to figure it out, like why exactly we need a whenever framework. So it is quite very much evident that any of the existing scoring classifier will only give you a point prediction, but here you will be getting a value of the P0 and P1, which really helps you in understanding what is the prediction boundary, which are more reliable in decision making. Another advantage of using Villanova framework is that you can use any of your machine learning taxonomy. So our approach is quite simple. So from the given flow diagram, the most important thing what we need to understand is that we need to find the degree of the badness of a particular rate group, like combining all the values from each of the disk drive. And once we get that value is passed to the variable sparing mechanism engine, where all the decisions are being taken. So now, before I jump in to discuss more about how exactly we have implemented this dynamic drive sparing, I will take a couple of seconds to make you understand that how exactly the prediction boundary will be used. So in the diagram, what you can see is that we have a green. So those you can think of it like a P0 value, which are the lower boundary, and the red one, which are the upper boundary. The difference between the value of P1 and P0 quantify the prediction uncertainty, which is used as an input for decision making. Now let's deep dive into the proposed mechanism for dynamic hot sparing. The diagram is a variant of an existing sparing mechanism where we introduce dual purpose node, which act like a spare drive as well as capacity drive. So the switching between the spare drive and the capacity drive is all dependent on the overall health of the rate group. And how we find exactly the number of the dual purpose disk required is by finding the difference between the maximum number of the spare node and the minimum number of the spare node. And we also introduce this address enabling latch, which will just, it's like a switch on and off button for the dual purpose node. The flow diagram describes how the dual purpose disk will be used in the sparing mechanism. So usually we will be having two use cases. The first one is where the minimum number of spare are sufficient, and the second is when the minimum number of spare are not sufficient. And the two cases arises just because of the overall health of the rate group. Let's have a look over the first use case where the minimum number of space are sufficient. So here, if you see the disk labeled as Y, which is a dual purpose disk, what we do here is that we enable the addressability from the AEL, that is the address enability latch, and we convert it from the spare to the disk drive. So this can be used like a generic disk drive in the existing rate. Now coming back to the second use case, when the number of the minimum spares are not sufficient, What we do here is that the dual purpose disk, we try to convert it from a capacity disk to a spare drive. How it is done is that first we try to copy the data of the existing dual purpose disk to the existing capacity drives in the RAID row, and then after we release that disk to the spare pool where we name it like a augmented spare. So this is how the both use cases where the minimum and the when the minimum number of spares are sufficient and when the minimum number of spares are not sufficient are handled using the proposed sparing mechanism. With this, I will hand it over to Hemant.
So as we saw that the proposed mechanism is going to help us quantify the degree of badness for a particular drive and then hence help to do a calculated decision of whether we would want to have those drives being used as spares or make them um, as capacitor drives whenever they are not needed, and when the need arises, mark them as spares. And that's what helps in providing a dynamic structure to the overall storage subsystem. Now, what we are also planning as part of our future work or our augmented use cases is to be able to use these techniques that we just learned to have proactive dispatch of drives based on the degree of badness. And wherever we see that the degree of badness is quite severe, have the drives shipped much upfront versus if the degree of badness is not that severe, then have the dispatches delayed a little bit accordingly. Also look at how we could have predictive part forecasting, which can actually result in an efficient supply chain management, where you could actually forecast how many parts you would need quarter over quarter if you are possibly a device manufacturer. Also for the customer, it is going to lead into having much disciplined capex where they don't have to worry about having their capex budgets beefed up just to take care of exigencies. At the same time, we can have these to apply to identifying badness with any other system components, be it on the storage system or the server subsystems. Okay, and at the same time, we are also looking at how this could be used to have environmental conditions based badness analysis done, where certain areas, if the humidity or the temperatures are extreme, based on those we could actually look at how is the wear and tear or how is the components aging over a period of time with those environmental conditions playing out, and based on that be able to focus, be able to dispatch all of those done much proactively. I'm sure that whatever time we've had is too less to be able to discuss the proposed solution in detail, but we would be more than happy to take any questions that you may have. And then let's assume we are not able to cover all the queries as part of this session. Feel free to reach out to us at the email addresses mentioned here. We are hopeful that these learnings that we've been able to share with you all, you find it helpful. And as part of that, we would also like to hear from you on the feedback for this session. Thanks and have a good day.